Okay, so I want to investigate here Poncelet trajectories on a concentric pair of ellipses, as you see here, and I want to be able to tilt the inner ellipse. So let's tilt it a little bit. I'm going to tilt that guy a little bit, and I'm going to investigate what a Poncelet trajectory does when I have a concentric pair and the inner ellipse has semi-axes which are tilted with respect to the outer one. So as you iterate, you do the Poncelet iteration, you're probably going to fill the space, right? Now, of course, I can change the aspect ratio of the inner ellipse. Let's change its the B prime, the minor semi-axis a little bit to see what happens to these trajectories. You saw that I went through something here that looked like it's close to being a periodic trajectory. And I can keep doing this, and I can make my inner ellipse be pretty skinny. Right here, I'm also pretty close to something that looks like a 3-periodic, which is, by the way, the subject of this video. But let's keep making this guy be skinnier and skinnier. So we can make it become quite skinny. Then you can go through a range of phenomena here, periodic phenomena. Okay, very good. I can also play with the other semi-axis. I can play with this A semi-axis. I can make it become less eccentric, become closer to a circle. And I can watch what's happening to the Poncelet trajectories. Here's one that is pretty close to being some sort of self-intersected Poncelet trajectory. Okay, so I actually want to bring down the number of rays to just 1. Let's go back to 1. And let's make this inner ellipse be a bit more fleshy, something like that. Okay, now as I said before, I can play with its angle, okay, and I can do other things we're going to cover in this video. Okay, now what I'm interested in is find out if this particular arrangement is going to close in 3 segments. So let's go ahead and iterate this once and a second time. Now you can see that this thing doesn't close, right? My third segment does not go back to P1, so this is not going to give rise, probably not going to give rise to a periodic trajectory. It might, but we would be lucky and it would be something like that, self-intersected. Okay, now there is something called a Cayley condition, okay, and I'm actually reporting here the non-adherence to the Cayley condition. So this value here will be 0 if this trajectory closes. So what I'm going to do now manually is this Cayley error. I'm going to tweak the position of my inner ellipse in such a way that that closing segment there coincides with P1. And I want you to watch what's happening to the Cayley error. So as I cross through P1, my Cayley error goes from negative to positive. So there's a root to this Cayley error right at the closure situation. So since I cannot do this manually, I'm going to actually run an optimizer by clicking on this button down here, which is going to optimize the tilt of this concentric ellipse while maintaining its semi-axis in such a way that this 3-periodic trajectory, or this 3-segment trajectory, closes. So there you go. I've ran the optimizer. My Cayley error now is 0. It's optimizing the Cayley error. And now I have a closed trajectory. So I can move P1 across the boundary, and I'm going to, by virtue of Poncelet's theorem, maintain the 3-periodic nature of this system. Now let's do another experiment. I'm going to displace the center of this ellipse to the right and a little bit to the top. So let's do that. I can translate this ellipse. Immediately, as I move away from the center, notice that the trajectory no longer closes. Okay, so as soon as I move away, my trajectory is no longer closing. And I'm just kind of, for the purposes of generality, I'm going to move the center up a little bit as well. So I'm going to put my inner ellipse, I'm going to make it a bit smaller, a bit less wide, so it fits within the outer ellipse. So now I have the situation. Again, I have a disparity between where I start and where I close. So a question I want to ask is, first of all, to see this visually, is if I rotate this ellipse with respect to its center, can I find a tilt that is going to close the trajectory? Let's see. Yes, I can. So there's a particular tilt there that is going to make my Cayley error vanish. So I'm going to run my optimizer again so that the system automatically finds what the tilt is. So there it is. Okay. So now I can do the same game. I can move my P1 around, and I can notice that for this more general position kind of situation, I can find a Poncelet trajectory that closes a 3-periodic family of Poncelet trajectories. Okay, now let's do another experiment. I want now to enforce that this inner ellipse is a circle. And I want to maintain its position right here. Can I? Let's try it. Okay, so now my optimizer has found a solution whereby the inner ellipse is a circle and I have the 3 periodic condition. What happens if I change, for example, the aspect ratio of the outer ellipse? You can see now that my 3 periodic no longer changes. Is there a circle centered here that would make a 3 periodic family exist? Let's run this optimizer. There it is. It's a circle with a slightly smaller radius.